Hello everybody. Today I'm going to be talking to you about our dangerous world. My name is Dr. Anna Bourne and I'm a senior lecturer in physical geography here at the School of Geography at Queen Mary, University of London. My research specialisms are in volcanic ash and using volcanic ash in records of past environmental change to establish the synchronicity of past environmental and climate changes. This image here is of me in a freezer in Copenhagen holding a piece of the Greenland ice cores. I've done a lot of research on finding volcanic ash layers that are hidden within the ice cores and using these to see whether climate change over the Northern Hemisphere over the last 100,000 years has been synchronous or not. This image is what volcanic ash looks like under a microscope. I'm currently working in the South Pacific in using lake records like these. This is a lake in Samoa, and this is a core that's been drilled through the lake. And I'm using the presence of volcanic ash layers like these dark bands just here and here in these sediments to look at the impact that volcanic ash has had on landscapes and people in the past. And I also use the presence of these volcanic ash layers to help us improve our knowledge of eruption frequencies for different volcanoes at points in the past. So this image is known as the Blue Marble. It was taken from space by the crew of Apollo 17 in 1972, and it's one of the most viewed and reproduced images in human history. What I want to do throughout this talk, Our Dangerous World, is introduce you to some topics that you would build upon throughout your degree here at Queen Mary. Through first year modules such as Geography in the World, all the way through to my own third year module, which is called Volcanoes, Climate Change and Society. So what comes to mind when you hear the title of this lecture, Dangerous World? I'll just give you a couple of seconds to think about that. What I mean when I say dangerous world is different types of events that could pose hazards to human society. And we've got some examples of these on the screen here. We have things like meteorological hazards, which is a hazard caused by short-term extreme weather and atmospheric conditions such as hurricanes or tornadoes. We've got geophysical hazards, which is a hazard originating from the solid earth. So this is where volcanic eruptions come in, and also things like earthquakes. We then have hydrological hazards. So this is hazard caused by the occurrence, movement and distribution of surface and subsurface freshwater and saltwater. So a common hydrological hazard is flooding. We have things like climatological hazards, which is a hazard caused by long-lived atmospheric processes ranging from intraseasonal to multi-decadal climate variability. And this includes things like wildfires and droughts. And then we have biological hazards. This is a hazard caused by exposure to living organisms and their toxic substances. So this bottom example here, we have a mosquito. So malaria is an example of a biological hazard. And then finally, we have technological hazards. So these are often more man-made hazards and includes things like industrial accidents, transport crashes, explosions. And so in this talk, I'm going to review some of the things that make the planet that we live on dangerous to human society. I'm going to look at what we mean when we say a hazard. We're going to focus a little bit on volcanic hazards because volcanoes are my particular area of interest and expertise. And then to finish off, we're going to have a think about whether the Earth itself is most dangerous or whether we as people living on the Earth are one of the biggest hazards to our own kind of continued survival on the planet. So when we're talking about events that may pose a hazard to humans, what do we mean by those terms? So an event or events are natural or man-made processes. They become hazards once they threaten to affect society and or the environment adversely. A hazard is therefore a natural event that is a potential threat to people and the things that they value. And a hazard becomes a disaster where a singular or interactive hazard has a profound impact on local people or places, either in terms of loss or life, injuries, property damage or environmental impact. and disasters are declared once a threshold of impact has been crossed, so for example, more than 10 fatalities. So to give an example of the difference between environmental events, hazards and disasters, we can look at the two images on this slide here, which both represent volcanic eruptions or the potential for volcanic eruptions. So the first is the 2012 eruption of Pagan Island. Pagan Island is now an uninhabited island that forms part of the Mariana Islands in the Pacific Ocean. It was inhabited until 1981, when an earlier volcanic eruption saw all people evacuated from the island. The eruption in 2012 was not explosive, so the products of the volcanic eruption didn't spread very far away from the island itself, and therefore this event caused no real hazard to people or to the things that they value. So it was just a natural event. However, in this example here, we see Mount Vesuvius, which lies in the Naples region of Italy. Any future eruption of Mount Vesuvius would be a hazard and also a potential disaster. There are 600,000 people that live in the red zone surrounding the volcano, and a large eruption has the potential to destroy the city of Naples. Therefore, any future eruption of Vesuvius would be a hazard, and as I said, would be have the potential to cause a disaster. For something to be called a disaster, for it to be entered into something called the Emergency Events Database, at least one of the following criteria have to be fulfilled. And the first time I looked at these criteria, I was really surprised at kind of how low the threshold for a hazard or an event to become a disaster is. So for the criteria of a disaster to be fulfilled, 10 or more people have to be reported killed, 100 or more people have to be reported affected. There has to be the declaration of a state of emergency or a call for international assistance. So at least one of those four criteria have to have been fulfilled for a disaster to be entered into this global emergency events database. And I looked at this database when I was recording this lecture last week, and we can see all of the figures for disasters between the start of the database in 1900 and the 12th of January 2023. And these are broken down into those categories that I talked about earlier. Biological disasters, climatological, geophysical, hydrological, meteorological and technological, with the addition of extraterrestrial. This would have been a meteorite impact on the Earth. So we can see that there's a big difference in the number of disasters that have occurred, with technological disasters, so man-made disasters, being the most frequent, but of the natural disasters, hydrological disasters, so this is things like flooding, and then meteorological disasters, things like hurricanes, being the most frequent. And we can see that represented graphically on this graph here. So again, technological disasters are responsible for the greatest number of disasters, followed by hydrological and meteorological. Things like geophysical hazards, so volcanoes and earthquakes, that I think you probably might expect to be more frequent than they are, or cause more disasters than they are much, much lower than hydrological and meteorological disasters. And biological and climatological disasters are at a similar level. When we then consider the impact of these disasters, and we can look at the impact of disasters by looking at the number of deaths or fatalities that are caused, but also the number of people affected. When we look at deaths, we can see that actually, despite causing or having the largest number of disasters, technological disasters don't account for anywhere near the most fatalities. And neither do hydrological or meteorological. Most fatalities come from biological and climatological disasters. So this is again things like malaria, dengue fever, Ebola. In the biological disasters and climatological things will mainly be famine, famine caused by drought, things like wildfires. And then lastly, if we go on to look at the number of people affected, we again see a different pattern. So here, hydrological disasters, which were the most frequent number of disasters on the natural scale, are responsible for affecting the most people. And then climatological disasters, despite not being as big in number, again, cause an impact on a lot of people. So all of these natural processes have the potential to cause to be a hazard to human society. We're now going to look in a little bit more detail at volcanic processes and see how volcanic processes occur, the types of hazard they cause to humans, and what we can do to manage some of those hazards. There are 596 active volcanoes in the world, and currently an estimated 800 million people live within 100 kilometres of a volcano that has the potential to erupt. It's therefore really important to understand volcanic processes, the hazards that these volcanoes pose, and the impact that any volcanic eruption is likely to have. On this figure here, we can see the cumulative fatalities caused by volcanic eruptions, and then time on this axis in 5-year windows. And we can actually see that a small number of eruptions, in this case these 5 eruptions, are responsible for a large proportion of the total fatalities. So the total fatalities of all eruptions is around 300,000. When you remove those 5 eruptions responsible for the most fatalities, we see this blue line here, and this takes us to around 100,000 eruptions. So 5 eruptions are responsible for around 200,000 deaths. So single events have the potential for devastating mass casualties at one moment in time. And it's important that actually these eruptions are not always the largest volcanic eruptions, and the impacts are not always proximal or close to the volcano. For example, the moderate-sized eruption of Nevado del Rey in Colombia in 1985 is this eruption here. It's responsible for over 23,000 fatalities. This eruption triggered lahars, which are volcanic mudflows, which resulted in the deaths of more than 23,000 people tens of kilometres from the volcano. So volcanic events can affect people in areas that aren't necessarily close to the volcanoes themselves, and single events can cause mass devastation rather than every event causing major fatalities. There are lots of different types of volcanic eruptions, and the varying styles of volcanic eruption often pose different hazards to people. So volcanic eruptions and eruptive phases are traditionally classified according to a wide range of qualitative criteria, and many have been given names from volcanoes where a certain type of behaviour was first observed or where now most commonly occurs. So the common eruption types are listed here, and these are presented on this diagram here, where at the bottom we have the height of the eruption column from smallest on this side to largest on this side. And on this axis we have explosiveness, from the lowest amount of explosiveness to the highest amount of explosiveness. So down in this bottom corner we have Hawaiian eruptions. These are typically what we call effusive activity. There isn't a large eruption column and they're not very explosive. Moving to a slightly bigger eruption column, we have Strombolian eruptions. These have a slightly bigger eruption column and are slightly more explosive. Going up both scales again, we see first subplinian eruptions and then plinian eruptions. Vulcanian eruptions have a similar height eruption column to subplinian, but are a little bit more explosive. And at the top of the explosivity, but with varying eruption height columns, we have Circean eruptions and Phreatoplinian eruptions. Both of these types of eruptions are where the magma interacts with water, and this is what causes them to be really explosive. So these different types of eruptions will cause different hazards, and that's why it's important to understand the type of volcanic eruption that occurs in different areas. So now we're going to look at the different volcanic processes and how they cause hazards. And we're going to begin by looking at volcanic ash and tephra. On this figure here, we can see that tephra is anything that is erupting out of the volcano. So it is pieces of pumice or large blocks or bombs, right down to the really fine volcanic ash. This is anything less than 2 millimeters in diameter, and it's the ash that can be transported a long way from the volcano. This is an image of ash burying cars and buildings after the 1984 eruption of Rabaul in Papua New Guinea. You can see this is some kind of minivan and there's ash halfway up the side of it. The 2010 eruption of the Eyjafjallajökull volcano in Iceland caused serious disruption to air traffic in the North Atlantic and Europe, as fine volcanic ash in the atmosphere drifted thousands of kilometres from the volcano. The resulting global economic losses from this moderate-sized eruption accumulated to around $5 billion as global businesses and supply chains were affected. This is another example of how a volcanic eruption can cause hazards close to the volcano, like we can see in this photo here, but also the ash from an eruption can cause disruption and hazards over a much, much wider area and lead to significant economic losses at the same time. The next process and hazard are pyroclastic flows, surges and blasts, and we can see this on the figure just here. These are the most lethal volcanic hazard, and they account for a third of all fatalities. They destroy nearly everything in their path. They cause severe damage to infrastructure, vegetation and agricultural land. Extreme temperatures can ignite fires and melt snow and ice. On the margins of pyroclastic flows, death and serious injury to people and animals may result from burns and inhalations of hot gases and ash, and they can lead to secondary hazards such as flooding and lahars. So lahars are shown just here. They are fast-moving mixtures of volcanic debris and water. They commonly occur when intense rain moves loose volcanic rock during an eruption, and they can also be caused by volcanic activity melting ice caps and glaciers. Lahars can threaten an area for years after an eruption. Lahars can crush, abrade, bury and carry away almost anything in their paths. By destroying bridges and roads, they can also trap people in areas vulnerable to other hazardous volcanic activity. Lahars are typically confined to valleys, as we can see in the diagram here, and areas close to the volcano, so we can identify vulnerable areas and put in place evacuation plans as needed. Our next hazard are debris avalanches and landslides. Landslides are large masses of wet or dry rock and soil that fall, slide or flow very rapidly under the force of gravity. They're really common in volcanic cones because they are tall, steep and weakened by the rise and eruption of molten rock. They're also constructed from poorly consolidated deposits. Landslides can also cause the secondary hazard of tsunamis if the material that has slid down the volcanic slope enters the sea. Landslides again typically destroy everything in their path. We then have lava flows. Lava is streams of molten rock that pours or ooze from an eruption vent. They're often very slow moving, and because of this, deaths are uncommon because they move so slowly so people can get out of their way easily. So while they may not cause death or harm directly to people, they still are a hazard because they can destroy everything in their path. Lava can bury homes and agricultural land under tens of meters of hardened black rock. People are rarely able to use land buried by lava flows, and they can't sell it for more than a small fraction of its previous worth. So while they don't directly affect people through death or injury, they affect people's possessions, and therefore they can also be considered hazards. We normally see lava flows in places where effusive volcanic activity is common. So there were large lava flows seen in the recent eruption in Iceland. The lava was flowing fairly slowly and lots of people could get quite close to the volcano and see the eruption happening. And it's also typical of Hawaiian volcanic activity. The final hazard that we're going to look at is volcanic gases. So magma contains dissolved gases which escape during the reduction in pressure as the magma moves towards the surface. We can see the gases that are contained within this eruption cloud here. The largest composition of the gases is water vapour, which accounts for between 60 and 99% of the gases. We then have carbon dioxide, which is up to 10%. Sulfur dioxide and other sulfurous gases makes up to 15%, and the halogens, including chlorine, make up 5%, up to 5% of the gas composition. Most of the hydrogen chloride and hydrogen fluoride are dissolved in the water droplets in the eruption cloud, and these quickly fall to the ground as acid rain. The most significant impacts from these injections come from the conversion of sulfur dioxide into sulfuric acid. This condenses rapidly in the stratosphere to form this fine veil of sulfate aerosols. The aerosols increase the reflection of radiation from the sun back into space. So we can see here radiation coming from the sun And the presence of this aerosol cloud reflects that radiation back into space, and therefore it has the effect of cooling the Earth's lower atmosphere, or the troposphere. The eruption of Mount Pinatubo in the Philippines in 1991 ejected a 20 million ton sulfur dioxide cloud into the stratosphere. It's still the largest sulfur dioxide cloud ever observed in the stratosphere since the beginning of such observations by satellites in 1978. Sulfate aerosols that formed in the stratosphere from the sulfur dioxide from the Pinatubo gas cloud increased the reflection of radiation from the sun back into space. And consequently, the Earth's surface cooled in the 3 years following the eruption by almost a degree at the height of the effect. So we can see on this slide here the percentages of all fatalities caused by the different volcanic hazards. And this is when we're looking at all fatalities. We can see that pyroclastic density currents are responsible for 33% of the fatalities. Followed by indirect hazards. So indirect hazards are things like famine, disease that are caused as people are displaced after a volcanic eruption. Then we see waves and tsunamis responsible for 20% of all fatalities, and then primary lahars for 14%, tephra for 3%, and secondary lahars. So these will be lahars that occur sometime after the volcanic eruption, also responsible for 3%. So it shows that both primary hazards like pyroclastic density flows or currents can have a big impact, but also secondary hazards such as things like famine after an eruption are really important when we consider the impact of volcanic eruptions. Volcanic eruptions are typically preceded by days to months of precursory activity, unlike other natural hazards such as earthquakes. So 50% of stratovolcanoes erupted after around a month of reported unrest. Therefore, we have a chance to monitor volcanoes in their normal state and therefore detect and recognise any changes to what is considered normal for that volcano. And this lets us recognise those warning signs and provides us with the best means to anticipate, plan for and mitigate against any potential disasters. Volcano observatories play a key role in this monitoring and early warning due to the localised character and individuality of volcanoes around the world. Volcano observatories have been set up on all or almost all active volcanoes that threaten the human population, and they're designed to monitor and potentially predict the eruptive volcanoes. This figure here shows a suite of tools that are available to the volcano observatory to help monitor the state of that volcano. It includes ground-based monitoring programs for active volcanoes, such as a network of seismometers that will detect volcanic earthquakes that are caused by magma movement. There'll also be a ground deformation network using things like tilt meters and global positioning systems to measure the rise and fall of the ground surface as magma migrates in the subsurface. We can also measure the gases that are emitted from volcanoes. This can either be done using remote sensing assessment of gas emissions into the atmosphere or by direct sampling and analysis of gas and water that's emitted from the summit and the flanks of the volcano. And then lastly, we can look at other kind of remote sensing techniques and observe volcanic activity using things like webcams and thermal imagery. And finally, we can measure other geophysical properties using tools such as strain meters, infrasound, and environmental indicators such as groundwater levels. So instrumental monitoring is the basis of early warning, forecasting and scientific advice to decision-making authorities. What we're going to look at now is a case study from the Mount St Helens eruption in 1980. So this is a photograph of Mount St Helens before it erupted in May 1980. It's a typical stratovolcano. It's a very picturesque image, if I do say so myself. The eruption of Mount St Helens was the first major eruption in the USA in the era of modern science. At the time, Mount St Helens was one of the most intensively studied and monitored major eruptions ever. However, it was highly unusual. Because there hadn't been a major eruption in the US for a long time, there was a lack of knowledge and experience, plus an underestimated level of public risk meant nearly 60 people died when the volcano underwent a massive explosion on May the 18th, 1980. There was a meeting in March of that year that developed a coordinated plan for a volcanic eruption from Mount St Helens, and this was led by the Forest Service. Many of the resources and communication protocols that we use for dealing with forest fires were put into place, things like planes in the area, roadblocks, 24-hour communications, radio and TV briefings. Agencies and scientists that influenced decisions and responses included the US Forest Service, the United States Geological Survey, the University of Washington Seismology Department, the state government, local government, the Federal Aviation Authority, and utility companies. There was precursory activity for several months that was taken seriously. So there were many earthquakes in the lead up to this eruption. But despite this monitoring and despite these plans put together by all of those agencies, 57 people were still killed and 2,000 people were forced to flee their homes. So how did that happen in an eruption that was supposed to be kind of well dealt with and where there was this precursory activity? This slide here shows visible changes to the volcano that occurred in the run-up to the eruption. So there were still these warning signs. This is series of photos shows what's known as the growth of the bulge. So this is the volcano in 1964. This is the volcano in March 29, 1980. And it's this area here that we're interested in, because this is where we start to see ground deformation as we proceed through April. April the 10th, April the 26th. And by May the 2nd, here there's a definite bulge. There's definitely been some movement underneath the ground surface. So there are these warning signs. So how did we still have people dying after this eruption? There were tourists in the area who were interviewed and they said they wanted to see the volcano erupt. They'd heard about the precursory activity. It was viewed as entertainment. There was poor risk judgment and a general lack of information. Local people were aware that there was a heightened risk from the volcano, but they just wanted it to quieten down so they could get on with their lives. And loggers and logging companies wanted to keep operating on the north side of the mountain. There are many logging roads on the mountain and on the volcano, which meant that it was hard to control illegal access despite roadblocks. Local funding was also soon exhausted. On May the 16th, which was a Friday, there would have been hundreds of loggers in the forest, despite warnings that the volcano may erupt. On May the 17th, which was a Saturday, 500 people went up to Spirit Lake with the authorities' permission to check out their properties. So the authorities let people go up the flanks of the volcano just to check on property. The volcano erupted on May the 18th, which was a Sunday. This and the fact that agencies were excluding most other people kept the death toll down to just 60, but it was still probably 60 too many. So there was probably, whilst plans were in place, there was probably just a general lack of information or a lack of understanding from people like the loggers and tourists and the general population of how serious an event of this kind could be. So despite the fact that there had been a couple of months of precursor activity, there was no immediate precursor reactivity. There was a magnitude 5.1 earthquake that occurred at 8:32 a.m. on May the 18th, 1980. And this was accompanied by a rapid series of events. At the same time as the earthquake, the volcano's northern bulge that we saw in that last series of images, the bulge and the summit slid away as a huge landslide. It's the largest debris avalanche ever recorded on Earth's in Earth's recorded history. A small dark grish ash column, which you can see here, rose directly from the base of the debris avalanche scarp. This landslide removed Mount St Helens' northern flank, including part of the cryptodome that had grown inside the volcano. The cryptodome was very hot and highly pressurized body of magma. And this bulge led to this giant landscape. So the eruption came out sideways, and essentially there was a large pyroclastic flow coming from the side of the volcano and then running down the rest of the flanks. The removal of that bulge resulted in the immediate depressurization of the volcano's magmatic system, and this triggered powerful eruptions that blasted out of the side of the volcano, and it also removed the upper 300 meters of the cone of the volcano. This lateral blast devastated an area of nearly 30 kilometers from west to east and more than 20 kilometers going northwards from the former summit of the volcano. In an inner zone extending nearly 10 kilometers from the summit, virtually no trees remained of what was once dense forest. Just beyond this area, which is where this photo was taken from, all standing trees were literally blown to the ground by the force of this blast. And at the blast's outer limit, the remaining trees were thoroughly seared. There was a 600 kilometre square devastated area that was blanketed by a deposit of hot debris carried by the blast. The removal of the cryptosome and the flank exposed the conduit of Mount St Helens, which resulted in a release of pressure at the top of the volcano's plumbing system. Less than an hour after the start of the eruption, this loss of conduit pressure initiated a Plinian eruption that sent a massive tephra plume high into the atmosphere. And we can see here the ash plume and how far the ash plume spread around continental USA. The Plinian phase of the eruption continued for 9 hours, producing a high eruption column, numerous pyroclastic flows, and ash fall downwind of the eruption. Over the course of the day, prevailing winds blew 520 million tons of ash eastward across the United States and caused complete darkness in areas of Washington, 400 kilometers from the volcano. Major ash falls occurred as far away as central Montana, and ash fell visibly as far eastwards as the Great Plains in the central United States, more than 1,500 kilometers away. The ash cloud spread across the USA in 3 days and circled the Earth in 15 days. So a huge impact from an eruption and from a volcano that was fairly well monitored. During the first few minutes of the eruption, parts of the blast cloud surged over the newly formed crater rim and down the west, south, and east sides of the volcano. The turbulently flowing hot rocks and gas quickly eroded and melted some of the snow and ice that was capping the volcano. And this created surges of water that eroded and mixed with loose rock debris to form lahars. Several lahars poured down the volcano into river valleys, ripping trees from their roots and destroying roads and bridges. This photo here shows one of the longest debris avalanches ever observed that flowed away from the mountain 23 miles down the Tolt River. And this was followed by lahars or mudflows, which had melted the snow or ice and then flowed over that debris avalanche and even further downstream. This is what the volcano looked like before the eruption and after, with most of the side of the volcano removed where that bulge had been, and also the top of the cone. This eruption had a big impact on the United States, not just because of the deaths that occurred. After this, it was decided that a permanent volcano watch was needed for the volcano, and the Cascades volcano observatories were established. It was decided that there needed to be a designated lead agency for emergencies, and that there had to be a clear federal emergency plan to deal with volcanic eruptions. So this really shows how we can learn from eruptions and use information to develop contingency plans. So that's been a little look at volcanic eruptions and some of their hazards. And just to end today, I want to consider whether it is these natural hazards that we've talked about that make our planet a dangerous world, or is it perhaps us as people living on the planet that are the biggest hazard to our continued survival? And while you think about that, I'm just going to show you this slide. This shows socio-economic trends from 1750 to 2010 in globally aggregated indicators for socio-economic development. So we've got things here like population, real GDP, primary energy use, urban population, large dams, water use. And shown in the dashed line is the year 1950. And for almost all of these socio-economic indicators, we can see this exponential rise that occurs after 1950. Population increases, GDP increases, fertilizer consumption increases, tourism increases, paper production increases. And with this associated rise in socioeconomic development comes the changes to the Earth system trends. So here we can see trends from, again, 1750 to 2010 in indicators for the structure and functioning of the Earth system. And again, we can see the dashed line that shows us when 1950 is. And we also see things like carbon dioxide concentration rising almost exponentially, emissions of methane, nitrous oxide, ocean acidification, shrimp aquaculture, the number of marine fish captured, tropical forest loss, stratospheric ozone depletion, which clearly has leveled off in recent years. So we can see this big link between our own socioeconomic development and detrimental impacts to the functioning and structure of the Earth's system. And one way we can look at this is to look at the planetary boundaries. The planetary boundaries approach aims to define a safe operating space for humanity with respect to the Earth's systems, and the planetary boundaries are associated with the planet's biophysical subsystems or processes. Rockstrom in 2009 tried to identify the Earth system processes and associated thresholds which, if crossed, could generate unacceptable environmental change. There are 9 such processes which they believe are necessary to define the planetary boundaries. These are climate change, rates of biodiversity loss in both terrestrial and marine systems, interference in the nitrogen and phosphorus cycles through biogeochemical flows, stratospheric ozone depletion, global freshwater use, change in land use, chemical pollution, and atmospheric aerosol loading. If these thresholds are crossed, then important subsystems, such as the monsoon system, could shift into a new state, often with disastrous or potentially disastrous consequences for humans. This is an updated version of Rockstrom's figure produced by Stefan et al. In 2015. And it shows if it's green that indicator of that planetary boundary is below the boundary, so it's in a safe condition. If it's yellow, it's in this zone of uncertainty, there's increasing risk. And if it's red, we are already beyond the zone of uncertainty. We have crossed that planetary boundary and there is a high risk. So where there are question marks, the kind of thresholds that are safe haven't been defined yet. We can see that nitrogen and phosphorus exceed the safe limit. Land system change is very close to it. Genetic diversity, so kind of biodiversity loss, has already well exceeded it. So if we're exceeding these planetary boundaries, what are the consequences going to be for people? So with us exceeding those planetary boundaries, we start to see environmental degradation occurring across the planet. Humanity is currently using natural resources far beyond the means of the planet, and at the same time millions of people face extreme human deprivation. So we need to tackle both of these crises together. Environmental stress can exacerbate poverty. Crossing planetary boundaries or their regional thresholds can push people back below the social foundation or prevent them from ever achieving it. And poverty can exacerbate environmental stress. People living below the social foundation may be forced to resort to using resources in an unsustainable way in order to meet their most essential needs. Globally, 2.7 billion people have no access to clean cooking facilities such as gas stoves, so rely on traditional biomass, including wood, dung, charcoal and crop residues, or coal for cooking. Women and children spend hours each day collecting the fuels, then inhaling their fumes over smoky fires, leading to an estimated 1.5 million premature deaths each year due to lung disease. Burning biomass produces black soot aerosols and carbon dioxide emissions, and the use of wood as a fuel can lead to local deforestation and biodiversity loss, further deepening poverty. So environmental degradation and human deprivation really go hand in hand and need to be tackled together. So when poverty and degradation meet, it creates a crisis for the worst off. And this is not a world that we want. So we need a vision that takes us away from this destiny. Can we devise a tool that allows us to plan for sustainable development within safe environmental limits? Is there a safe operating space for humanity? And this is an earlier version of the planetary boundary diagram I showed earlier. And if we look inside this green area here, this is where we have our safe operating space for humanity. This is the same diagram as the last one, but it just zooms in on that green circle in the middle of the previous picture. A safe operating space for humanity describes the Earth system conditions that are bounded by tipping points. So within this space, it might be environmentally safe, but it could be deeply socially unjust, leaving many people living in poverty and then facing extreme inequality. So how about the idea of adding on social boundaries to the picture? Just as there is an environmental ceiling above which lies unacceptable environmental degradation, so too there is a social foundation below which lies unacceptable human deprivation. But what should the dimensions of deprivation be? The top priorities that governments have raised form these 11 social dimensions, such as freedom from hunger, from income poverty and energy poverty, from gender equality, and from ill health and illiteracy. Between the social foundation and the environmental ceiling lies a space which is shaped like a donut, and this is the safe and just space for humanity. If economic development were inclusive and sustainable, it would bring humanity into this space and allow us to thrive there. So we can see this donut, as it's known, here. The challenge of moving into the safe and just space for humanity is complex because social and planetary boundaries are independent. Environmental stress can exacerbate poverty and vice versa, but well-designed policies can promote both poverty eradication and environmental sustainability, bringing humanity into the donut from both sides. On this side of the slide, we can see this same donut with our social foundation and environmental ceiling, and those factors of social dimensions in the middle here. But we can see added on there is how we're doing with each of the planetary boundaries. So kind of crossing it for climate change, for exceeding the boundary for nitrogen and phosphorus loss, land conversion and biodiversity loss, and how all of the other planetary boundaries are doing as well. So would eradicating poverty put planetary boundaries under stress? And we can think about these from some of those different factors. So food, providing the additional calories needed by the 13% of the world's population who face hunger would require just 1% of the current global food supply. With energy, bringing electricity to the 19% of the world's population who currently lack it could be achieved with less than 1% increase in global carbon dioxide emissions. This framework brings out a new perspective on sustainable development. The resulting space, the donut, is where inclusive and sustainable economic development takes place. It implies no limit to human well-being. Indeed, within this space is humanity's best chance to thrive. So we can hopefully all be working towards this safe and just space for humanity, where people are no longer such a threat to the environment. We're not pushing those planetary boundaries, but we're also living in that safe, just space where human development can continue to thrive. So that brings us to the end of today's Taster Talk. I hope you've enjoyed it. Today we have considered ways in which the Earth can be dangerous to the people that live on it. We've considered the differences between natural events, hazards and disasters, and we've looked at which types of disasters are most frequent and which affect people the most. We've looked specifically at volcanic processes and hazards and the impact that they have on people, looking at a case study of the eruption of Mount St Helens in 1980. And then finally, we've looked at the impact that people have on the planet. And are we perhaps the most dangerous part of the planet, and how we are causing us to exceed planetary boundaries? And then finally, we've thought about how we can go on living on the planet by living in this safe and just space for humanity. I do hope you've enjoyed this Taster Talk today and you enjoy the other talks that are available. Thank you very much for listening. Bye.